Hey guys, so this video lesson is going to focus on two-dimensional, or what's also referred to as projectile motion. So we focused on this a little bit with the kind of Captain America report and things like that, but we're going to dive a little more into it, get some more of the specifics as far as what projectile motion really means. So the agenda, we're going to talk what is two-dimensional projectile motion. Get a couple terms that are new. Some are pretty similar to terms we've used before, but just kind of using them more specifically. Then there's going to be a quick video analysis using logger probe and object, and I've already done that, so I'm just going to kind of show you that video, what happened, how I got the information. Talking about then the vertical and the horizontal motion of that video analysis, and then focusing on all in the timing. So all in all, pretty short video. As you're doing this in GoFormative, watching the video, obviously. And then at different times I'm going to tell you to pause it and tell you to answer a few specific questions that are below. So making sure that you are watching the entire video and then answering the questions that go along with it. Alright, so let's get started. So what is two-dimensional projectile motion? Simply stated, it's just an object that moves horizontally and vertically at the same time. There are a lot of examples of things that experience projectile motion. Some you're familiar with, some you may not be familiar with. But for example, if a cannon, for example, is fired and it is launched at a boat in the sea, that cannonball will fly kind of across this path here. So it's going to move horizontally out in this direction, but it's also going to fall vertically in this direction, kind of doing that at the same time. That's why we see the curved path the way we do. We don't see the cannonball fall straight down or shoot straight out and keep going, but we see those kind of different things there. Oops, let's not do that. So if we zoom it back in, same thing if we have a really bad baseball pitcher who throws, or if someone throwing a slow pitch softball, we can see that path again. This time it's kind of moves up and then comes back down. So it does the same thing, goes up and then comes back down again, still moving out horizontally, but also rising vertically and then falling vertically as it moves to the right. Then one other example, and again there's plenty of examples, would be like a bow and arrow, again following that kind of arced path where it's moving horizontally, but also moves up and then comes back down towards the object itself. So you want to go ahead and pause the video and answer question 1, and then we'll kind of move on. Now, a few terms that we're going to talk about, and again, you can write these down in your notes so you have them with you when we talk about them further. But the first two are the ones that are the more like kind of important ones and things we want to distinguish between. So the first one is range, and how far, that means just how far a projectile travels horizontally. So the range, when we talk about that, like when we looked at the projectile testing you did on Monday, that's what you're kind of measuring, the range, how far the marble fell away from the table. So that's what we talk about. That's the term we're going to use. It's also referred to delta x when we look at our equations. That would be our symbol for range. So how far a projectile travels horizontally. Then height, which is delta y. So when we look at equations now, we're not going to use delta x all the time because we are going to have to talk about both horizontal and vertical directions. So height in this case is how far a projectile travels vertically, not horizontally, vertically. So for example, like with the ramps in class, those were your height. So how far the ramp was above the table where the marble fell from. So again, how far object travels vertically or falls vertically. And then time, pretty straightforward, how long it takes a projectile to fall. So how long does it, once it leaves the ramp or leaves, the cannon, leaves the bow, whatever example you want to use, how long does it take that object to reach the ground, regardless of how it's launched, whatever it might be. And then the last one we'll talk about is the launch velocity. Launch velocity, so how fast a projectile is moving kind of horizontally. So if it's initially launched from a cannon, from a bow, how fast is it actually moving horizontally? That's what we talk about with launch velocity. And again, just using v for velocity in that situation there. So now if you want to pause the video and answer questions 2 and 3, you should be good to go. Now, I've already talked over these videos when I recorded them initially, so I'm just going to let them play through, but I just kind of give you a heads up. So I'm going to play this first video, you see the one down at the bottom right, I'm then going to play that, so it'll be kind of like a little jump from that video to the next video as you watch them.
So now doing a video analysis of an object that is experiencing projectile or two-dimensional motion. We're going to look at a golfer here, and the golf ball is the object we're specifically focusing on. So the golf ball's been hit. So this video's been sped up a little bit, just to not take too much time. But what I've done, I set the origin, that's the yellow lines here, so kind of where the ball started. There's a green line, it's kind of hard to see here, but that's my scale, so like using the height of the golfer, I can kind of scale this, so that as I click, you see these blue dots on the position where the golf ball is, each time, so it advances at one frame. And what's happening, like kind of in the background, is Logger Pro is plotting these points on position, time graph, velocity, time graph, and everything kind of along with that. So we're going to kind of continue clicking here.
Now I'm going to move this other video up, make it a little too big there. So I've kind of finished clicking through all the points, and then I'm going to talk a little more about the graphs.
Now that I've got all the points kind of clicked out on the for the position of the ball on the graph, I'm going to delete the video. So I'm going to get rid of the video. It's going to still save my data in the background. So what I have here, right now I have position time. They're on the same side. The X, the Y position, so this graphs that position. The X is kind of a little different just because of the way the origin set up on the graph and the way I filmed it. But we're really not worried about that. What we're worried about is the velocity time graphs for the golf ball. So if we look at the X velocity, so the horizontal velocity, now right now that's pretty jumbled up and it's not really scaled as nicely as we like it. So let's scale this out a little bit. Let's auto scale larger. Auto scale larger. And let's go. That didn't work. Okay, just kidding. Let's go. Auto scale from 0. Auto scale from 0. Hit OK. Now we get all these points kind of down here in the bottom in this general region here. But if I kind of bring this up, like so if I scale it even more, kind of scale it larger a little bit, you can see all of those velocity values, and they're all over here to the right because the video, we only use like the last second and a half of the video when the golf ball's actually moving. But you can kind of see, we get a decent kind of horizontal line. Here we're going to put a best fit line. The best fit line would be pretty horizontal, meaning in the X direction, the object moves with a constant velocity. So when an object is moving with projectile motion, or two-dimensional motion, in the X direction, so left to right, it's going to move with a constant velocity. Now, if we switch that to the Y direction, so the up and down direction, I get this kind of graph here. I'm going to stretch this out just so we can see the time frame that we need. That's all we really need. So putting that in the center of the screen here, you can see that we have a velocity time graph. That shows an object that is slowing down because the velocity is moving towards 0 meters per second, and then it speeds up, which makes sense when I hit the golf ball in the air. It slows down on the way up, and it speeds up on the way down. Now if I highlight this region here, put a best fit line, we get a slope of about 11 meters per second, which is a little higher than we would like it, but it's close to our 9.8 or 10 meters per second for the acceleration due to gravity. So the slope of the velocity time graph, remember, represents acceleration, and so the object in the vertical direction is in free fall. So horizontally it's moving with a constant velocity, and then vertically it is in free fall, therefore it's accelerating at 9.8 meters per second. Again, just the way the video is, it's not scaled perfectly, so the velocity, the acceleration is going to be a little higher than we would need it.
So again, you can go ahead and pause the video here in a second. You're going to answer questions 4 and 5 and 6 eventually as we kind of move forward. But the key thing is talking about vertical and horizontal motions separately. But to kind of, don't pause the video, I lied, don't pause it. So if we kind of summarize everything, so the horizontal motion of the object in projectile motion moves with a constant velocity. It's going to move with a constant velocity in the horizontal direction. So the equations, any calculations we would do, we would just use our constant velocity equations. So the two that are over here. So we just use those two equations. Now our velocity time graph, just generally speaking, is going to look something like this. Let's make that a little bolder. So it's going to look something like this, where we have an object that's moving at a constant velocity. So we need a nice horizontal line on our velocity time graph. And then the vertical direction, the object moves with a changing velocity. So vertically, when an object's in in two-dimensional or projectile motion, it's going to move with a changing velocity. Specifically, that velocity, changing velocity, is free fall due to gravity. So our negative 9.8 meters per second. So we would use any calculations we would use our changing velocity equations, kind of the ones listed up there with our acceleration. And you can see here, here's the key thing. We now use delta y for the height in these equations, just paying attention closely to that. And then our velocity time graph is going to look again something like this, showing an object that is first, slowing down, and then it's going to then speed up. This graph could also be broken up, so maybe an object only moves upward. That's the only thing we're looking at, so we just have this part of the graph. Or maybe the object just speeds up, like it falls off a cliff or falls off a building, the object does, and we're only going to look at the speeding up portion. So it just kind of depends, but generally speaking, we just need to show an object with a changing velocity, and you can kind of look at the situation specifically. So now you can go ahead and pause the video and answer questions 4, 5, and 6. And we'll wrap this up. So the last bit, all in the timing, the key thing, the thing that kind of connects all of the horizontal motion equations to the vertical motion equation is the time. Because regardless of the situation, how fast the object's launched, what it's doing, it's going to hit the ground at the same time, like in the same spot. It's going to take the same time for the object to fall horizontally as it does vertically, because they're doing that at the same time. So if I have the time that it takes the object to fall, I can calculate basically all of the other variables. So if I know like the height and the time, I can get the velocity, and then I can use the time to get the other variables based on the acceleration and everything else that goes along with it. So that's going to be a key thing as we look at, some quantitative representations, that just knowing time is the thing that's going to move kind of between the two sets of equations. You can pause the video, hit, or just stop the video, doesn't really matter. Answer question 7, then make sure you hit submit on Go Formative. And if you could, depending if you're doing on this iPad or not, go to Google Classroom and say that you turned in this assignment, if you could, please, just so that I know kind of in both spots that it's marked and we're good to go. Other than that, have a great day and have a good night.